In the case of free-falling object, when it's thrown upward, so as you can see in here, you have a given ball, for example, that is thrown upward, which means that its velocity, it's pointing upward. It's a vector pointing in the same direction as y in this case. So since the velocity, it has a given value, the ball cannot keep moving upward for an infinite amount of time. So that's why the ball in this case reaches a given maximum height. And this happens when it's momentarily at rest. That means when its instantaneous velocity becomes zero at a given instant. And so this is why in this case, the motion will be described by kind of two parts. The first part when the object reaches its maximum height, and then it will go down under the gravity again. So please note that in both parts of this motion and during the full time of the motion, the gravity is all the time pointing downward through the vector g. Two comments about the general case. So here we have derived the equations for the position and the velocity as a function of time. So these two expressions, and we have seen also how to derive the velocity as a function of the position using the integration approach for the case of a particle moving under a constant acceleration. But this is a particular case of motion. In a general case, a particle does not necessarily move under a constant acceleration, and it could have an acceleration that is different than constant, so time dependent. So in this case, how can we derive these equations? Actually, we do the same for what we did before, but with a different strategy, in the sense that the starting point is the same. We start with the definition of the instantaneous acceleration being the derivative of the velocity with respect to time. This allows us to write down the dv equals a dt. If you take the integral on both sides, you end up with integral of dv is equal to integral of a dt. The only difference is that now you cannot actually get this a out of the integral because a is not a constant any longer, and you have to substitute a by its expression inside the integral so that you can calculate or derive the corresponding function. And if a does not depend on v, then you can make the integral of dv as vt minus v t0. So this is it for the velocity, and you can do the same as well for the position as a function of time. So you start with the definition of the velocity equals to the derivative of the position with respect to time. You take the differential of both position and the time, which are related through the velocity, and you make the integral on both sides. And all what you need to do now is to replace or substitute v with its expression, which you have derived earlier in the previous slide, which is in here. So in the general case, this is the strategy that you can use to derive the equations, the kinematic equations, velocity as a function of time, the position as a function of time, and the position as a function of the velocity, or the velocity as a function of the position. So this is it for this chapter.